All right, here we are. Module 4 is going to be the next module that we look at here in basic mechanisms. Module 4, as you can see, is going to be velocity analysis. So now we're going to be looking at not only how do things move around, but how fast are they moving? Okay. So in module 4 here, as we look at the learning plan, it is going to be broken up into a part 1 and a part 2. So part 1 is going to be today. And we're going to be looking at this handout throughout the lecture demos that we do. So if you happen to be in class, I did make a print for everybody. If you're virtual or watching this on the replay, you're going to need to print that out because we are going to have places that we're going to be filling in, and that's going to be part of what you're going to be handing in for the practice problems. Okay. So as we look back to our module, session recordings, I'll be populating here as we do those for this course. But as you know, I do have the previous years recordings, which do coincide with what we're doing here. So if you wanted to, refer to those, you're welcome to do that. And then you'll notice here that we have the two things that we're going to be handing in just like normal. Practice problems. As you know, practice problems are going to be the things that we demonstrate here in class. So we will have one example, which is going to be right at the beginning of our chapter, 6.1. And then we're going to have the handout and the rest of the practice problems. So we do have two things that you'll be handing in, if you would, for the practice problems. In addition, the couple things that I always ask you, what did you learn? And then what are some things that you feel you need to gain a little bit more confidence on? So when we get there, you won't be handing in the practice problems until we're through both parts of the demo lecture. Okay, so you'll know exactly. I'll kind of let you know when we're going to be having those items so that you can make sure to prepare those. And then you're going to notice that there is an assignment 4 here, assignment 4. Again, quite a few problems that we're doing, but don't worry. We'll kind of guide you through that. I'll prepare you as we're doing our lecture demos so that you feel like you know exactly what we're doing here. And most of these early ones are kind of small, okay? Just kind of preparing us. The later ones are the ones that probably have a couple more steps that are involved in them. So we'll look at those as we're able to or we're ready to. So I'm going to go over to Module 4. I'm going to pull up our PowerPoint presentation. And as you can see here, I'm going to just zoom out a little bit. This is going to be Chapter 6 in our textbook. So I know we're kind of moving around a little bit. We've done Chapter 1, Chapter 3, Chapter 4, and now we're going over to Chapter 6. So Chapter 6 is velocity analysis. Okay, velocity analysis. This starts on page 123 in your textbook if you want to open up to that. So our objectives here in Chapter 6 or in our velocity analysis module here are, first of all, we're going to define linear, rotational, and relative velocities. Okay, so understanding what those are, and then ultimately we're going to be applying them to different situations. So understanding when we use linear, rotational, and then also when we use relatives. Then we're also going to be converting between linear and angular velocities, kind of understanding how they're related to one another and then getting what we need for each one. We're going to apply the relative velocity method to graphically solve for velocities of a point on a link, knowing the velocity on another link. So this is when we have mechanisms that are joined by different pins, if you would, or they're operating as sliders. And we want to figure out what's going on. If I rotate my crank at a certain RPMs, what are the rest of the links on in my mechanism? What are they going to look like? What is the motion of those going to look like? So we're going to graphically be solving for those. All right. And then we're going to use that relative velocity method again to graphically solve for the velocities of any point of interest that are also on maybe a floating link or other links that we might have. Okay. So stuff to do. So first of all, when we start looking at velocity to us, and you guys have hit this in, different places, whether it's in, the primary grades as far as high school, middle school, science, physics classes that you've had. Maybe you've had physics already here along the way at WCTC. So velocity is how fast are points on a link traveling. Okay, how fast are they going? So the determination of velocity of a link is the purpose of this chapter. So just as the chapter says, it's looking at velocity analysis, but we're most specifically going to use the relative velocity method to get us there. And that's a graphical method. Just like everything else we've been doing, we've been kind of erring on that graphical side because you guys get a lot of analytical in other places, okay? Or the math application of. So starting with linear velocity is going to be the straight line displacement of a point per unit time. Now, in this book, they use the variable lowercase v for velocity, which is consistent with, other applications in engineering and science and such. Now they use r for the displacement. So for instance, what is the distance? That's not as common of a variable, and you're going to find that lowercase d is most often going to be the one, and we're going to reference that as well. I want it to be consistent with what you've learned before, but in this book, the displacement or the distance that would be traveled, they're using the letter r, but also you probably have seen it as d, lowercase d, most often. Now, velocity is a vector. Okay, we know that. We kind of mentioned that when we were talking about vectors in our last module, that velocity is one. But to fully define velocity, we need both its magnitude and its direction. So its magnitude is going to come from how fast am I going? All right, it might be in miles per hour. So I'm going 55 miles per hour, but it becomes a vector when we add on direction. Okay, I'm going 50 miles per hour north. Okay, now I'm a velocity. I'm a vector because I have both magnitude, how fast I'm going, what its speed is, and I know in what direction I'm going. Okay, north in this case. Now, when we talk about it, as we saw in module 3, we would draw vectors to a length that was then their magnitude, and then we would add an arrowhead and an angle to give it then its direction to fully define it. Okay, so we've already kind of set the groundwork or the foundation of applying vectors, and most specifically, we're going to be applying it to velocity in this particular module, this chapter. Now, rectilinear motion. Rectilinear motion is when we have motion that results in a straight line displacement. So I am just moving along in a straight line. That's rectilinear motion. Okay, so our first example and also the first problem for our practice problems is going to be example 6.1. So if we head over to page 124, up at the top of page 124, you're going to notice that we have a very simple problem. And this is a great problem to kind of just get us warmed up to the ideas here, that we're going to be looking at. So I grab a piece of paper. As part of your practice problems, this is the first problem that we're going to be working on, okay? And this is outside of the handout. As I mentioned earlier, we're going to be working a lot of the problems, I think all the rest, in the handout. But this first one, we're going to kind of, use what they have here. So in problem 6.1, we have a crate that's on a conveyor, as we can see here, all right? It's going to move towards the left at a constant rate, okay, at a constant rate. And it's telling us that it takes 40 seconds to traverse 25 feet, okay, on that conveyor. So they want us to determine the linear velocity of that crate, okay, the linear velocity of that crate. So as we know, as we got from the previous page, so this is example 6.1, okay, and again, it's on page 124. Okay. We know that if we want to find out what is the linear velocity, velocity is going to be equal to d over t. Now, I just want to preface that d is equal to r is equal to s is another variable that we end up seeing used quite often for distance. Okay, I'm trying to get it. I'm kind of in the crack of my book here. Okay, so whether it's a variable of d, r, or s, Rainer. You will see that, yeah. But right now, all we're saying is it's just going to move. So when we use the triangle, that just means what was the change in direction or the change in velocity. So you might see the triangle, and that's called delta. Delta is a universal symbol for when something changes, okay? In this case, we're just identifying, we're going to move 25 feet, okay? You could put that in as delta D, but a lot of times we see it just as D. How much distance did we cover over how much time it took us, okay? So DRS all kind of mean the same thing, okay? R they're using in the book, not as popular, but S and D are probably things that you've seen before, and I think we see S in the handout a little bit later, okay? T is going to be equal to time, okay? Lowercase t, and then V is going to be equal to velocity, okay? Now, this is calculating the magnitude of the velocity. Now, if you've had physics, you know that sometimes we interchange speed and velocity, but speed is fully defined by just magnitude. Speed is like looking at my speedometer and how fast am I going? What's the number? What's the magnitude? Velocity, again, is when I add a direction to it, okay? So when I have velocity, I'm expecting that I'm not only going to know its magnitude, and I calculate its magnitude by how much distance did I cover and how much time, I would also be looking at its direction, okay, or understanding or knowing its direction. Now, do I know the direction of the velocity in this case? If I look at the problem? Yeah, how do I know, Steve?
The arrow in the illustration.
Yeah, if we look closer at the illustration, it is representing the velocity with a vector, right? A line with an arrowhead on it, which we know is exactly how we would represent it because velocity is a vector quantity, okay? And we can see that the direction that it's going in would be horizontally to the left, right? So we have already its direction defined. Now this equation is giving us its magnitude, okay? All right, so to fully define it, we need both magnitude and direction. So in this case, we know that the distance we're going to cover is what from the problem? Zoom in here a little bit. Do we see any distance references in the problem that we have here?
25 feet.
Steve said 25 feet. Yes. Rainer, do you agree? Yes, 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 yes. So 25 feet is going to be equal to our distance. So whenever we show equations that we're writing out, you need to first tell me what is the equation you're going to use. So you want to show the equation in variable form, okay? And this is going to be not only for our practice problems, but for assignments that you hand in, okay, for me. Then what we're going to do is in the next line, if you would, we're going to say, okay, we're going to define everything that we can. So we know the distance is 25, and we're going to add the units, okay? So notice I have 25 feet in back of it, okay? So how long does it take me to cover 25 feet? Did it tell me in the problem? What did it say, Rainer? 40 seconds, exactly. So underneath the time over here is going to be 40 seconds. Now, a couple things I want to make sure that you understand. Number one, notice that this is a division. It's distance divided by time, okay? When you show this equation, always show it what I call it in fraction mode of up down, meaning do not show this as d divided by t as a slash. Do not do that, okay? I will take points off if I see that. And the reason being is that we are going to be adding in every phase of the problem the units. Okay, and when units combine or when they cancel, then I can see top and bottom, numerator, denominator, when they actually cancel. If I do it in the slash and I write it just as a solid line, I don't know what's on top and what's on the bottom to get the availability. Okay, you might say, I can keep track of that, but I don't want you to do that. Okay, so it's kind of like when your mom says, just because, okay? It's really not just because. It's really for a good reason of being able to see more clearly the cancellations that occur. Because then at the very end, before we then do our final math, this lets us know, did I set it up appropriately? Okay, so the next thing we need to understand are what are appropriate units for velocity. And I look back at my variables here. I look back at my equation. Velocity is equal to distance divided by time. So when I look here, if I have feet on top and seconds on the bottom, Units for velocity would be distance over time, feet per second, inches per second, miles per hour. Okay, any one of those would be valid. And as long as you're in that format where you've got distance on the top divided by time, it confirms that you set up your problem correctly. Does that make sense for everybody? Okay. I am certain that if you've had physics, right, or if you've had statics, or strength of materials, you've been doing kind of this work already, right? Putting your units in, making sure they cancel out properly, and that you end up with the appropriate units. So we're really being consistent with other courses that you've had before. So now if I do the math here, I'm going to say velocity is equal to, if I take 25 divided by 40, what's the number I get? 1 point something, right? Everybody should have their calculator out doing it. 1.625. Oh, I'm sorry. 0.625. Yeah, that's right. 25 divided by 40, right? And what are my units here? Feet per second, right? Nothing canceled out, did it? So in your final answer, what we don't want to occur is, for instance, if you left this as 25 divided by 40, okay? You would get points off because we don't have units magically appear. I want to see the units actually in the problem. Okay. And at times there will be cancellations and combinations of, but in this case, nothing canceled out. And then your final answer is going to have a box around it. My velocity is 0.625 feet per second. Okay. All right. And if we look and peek at our answer here, you'll notice that they ended up with that value of 0.625 feet per second. Now, you'll notice that they did a conversion here. Now, unless the problem says we want these units in inches per second, you don't have to do that final conversion, but that's all that they did at the very end here. They did one last conversion and they multiplied by 12 to get it in inches per second. Okay, but you could stop right here. Okay, not a problem. So that is our first practice problem that we're going to be handing in for Module 4. Any questions on that? And we'll continue to reinforce this as we, continue and do more problems. Okay. All right. So I'm going to go back to our PowerPoint presentation. And you'll notice here now it says we're going to now go to our handout. Okay. In this particular book, they do a great job, but I like to do some review of some concepts and showing you the relationship between rotational and linear velocities. Okay, you've gotten this in your physics classes, bless you, but it might have been a little while, and I just want to make sure that we're all on the same page. Okay, so what we're going to do is underneath our camera here, we are going to work out of that velocity analysis handout. Okay. So you'll notice that at the top here, the first page is kind of like an overview, right? And as we page through this handout, you're going to notice that there's going to be some problems here, some things to fill in. So that's why printing out the handout is most efficient. But if you don't have the ability to print out right now, you'll just have to make real clear the items that you're going to be handing in for me, because this will be part of the practice problems that you hand in. Okay. So up here, this is what we just talked about, linear velocity. Linear velocity is rectilinear points, so straight line motion. And velocity, its magnitude is going to be found by taking S or D, okay? So I'm going to say this is also equal to D over T, right? Distance over time, okay? So things like, how fast is a conveyor belt moving? A conveyor belt most often is going to have linear velocity. How fast and in what direction is a car moving? Okay. A person walking, a distance has rectilinear or linear velocity. So lowercase v, and then it's going to be distance over time, whether it's S, D, R as one of those variables divided by T. Okay. Now, as we look down here, velocities on a rotating link, okay? Velocities on a rotating link. So this is where we start looking at, okay, if we have something that's rotating, we're going to find out that we also have a component of that motion that is going to be linear velocity as well. So how are those related? So first of all, you'll notice that we see kind of our standard kinematic diagram numbers and callouts here. First of all, you'll notice that we have a frame right here, right? Frame just means that that point is not going to be moving. So anything that's attached to it is going to be, in this case, this link is going to be rotating about a fixed center at point A, okay? Link number 1 is going to be our frame, that non-moving member, okay? Now you'll notice here that I could have drawn a line, but I wanted to kind of make it clear that this is a link, okay, that is a length long, whatever that length is going to be, okay? It doesn't matter at this point, but this is going to be points that are on a rigid link, okay? And those points on that rigid link are all going to be connected to that frame member at A, and we've got points X, Y, and Z, okay? X, Y, and Z. And this link would be our link number 2. Okay, link number 1 is the frame. Link number 2 is attached to the frame. And we're only going to worry about this one link. We're not going to worry about a link 3 or a 4 at this point. Okay, just links number 1 and 2, a single link that is rotating about a fixed center. Okay. Now, it says here that link number 2 rotates at an angular velocity, which I always refer to as W2, but I believe it's the lowercase omega Greek letter, okay? So you see it as this lowercase W2, okay? And that W2 angular velocity is how fast am I rotating about that fixed center, about that center. So you'll notice that over here in the diagram, we see this like arc with an arrowhead, and it's labeled W2. So W2 is the angular velocity of link number 2. Angular velocity of link number 2. Now, what that means is that link is rotating about that center at this rate. Okay, this rate. That rate of W is going to be in revolutions per minute, radians per second, those types of units, which I'm sure you've come across in the past. And we'll kind of expand out about that. Now, every point on this link has angular velocity of the same number, okay? So point X has angular velocity of whatever W2 is. Point Z, point Y, all have angular velocity the same as whatever the magnitude of W2 is, okay? So this entire link, if I say it's rotating at 100 RPMs, that means it's going around 100 times per minute. Okay, revolutions, 100 revolutions per minute. And each one of these points is doing the very same thing. Point Z out here, point X here, everything on that link is going at that same angular velocity. Okay, so the angular velocity remains the same for the entire link. Okay, now, when we look at individual points, they not only have an angular velocity that they are because they're on the link, but they also have a linear velocity component. Okay, a linear velocity component. Now, linear velocity, we are going to represent as a vector. Okay, so we see those here. We see vector VZ, vector VY, and vector VX. And those are going to be the straight line velocity components of the motion that points X, Y, and Z have. Okay, all right. So we see that here. So Vx, Vy, and Vz. All right. Now, something you're going to notice here is that we identify them. So it's not just velocity of the link, right? Straight line velocity of the link. It's the velocity of link of the, the velocity of point X. So it's V sub X. When it's the velocity of Y, it's V sub Y. When it's the velocity of point Z, V sub Z. When it's the angular velocity of link 2, it's W2, okay? So we have to, first of all, be really consistent with labeling our points and our links so that we can add the appropriate labels then for the different variables that we're going to be looking at, like straight line velocity of individual points, and then angular velocities of a link, okay? Now, directions. The direction of the linear velocities are going to point in a straight line direction in the direction of rotation, but also perpendicular to their radius back to the center of rotation. So if we look here, you'll notice that our fixed center A. And if I draw a straight line, which happens to be, all the way through each one of these points, okay, this is going to be, this line right here is going to be the radius of rotation to that point, okay? So the radius of rotation to point X, the radius of rotation to point Y, and the radius of rotation to point Z, okay? The direction of the straight line velocity V is always going to be perpendicular to that radius back to its center of rotation. So from Z here, if I take a straight line and I go from Z back to A, the direction of the straight line velocity is perpendicular to that radius. Do you see that? Okay. Additionally, that gives us a kind of its line of action, but the direction that we are going to show the arrow is going to be in the direction of rotation. So we have to know the direction of W2. So W2 is going clockwise, right? So notice that VZ has an arrowhead going down and to the right at this point in time, if you would. Does that make sense to everybody? Okay. So if I know the direction of rotation of the entire link here, I know the direction of the straight line velocity component to be perpendicular to the radius back to the center of rotation, and it's going to be pointing in the direction of rotation. It would not be going up and to the left here. It has to go in the direction of rotation, okay? I see that very same thing for Y and for X, okay? Now, I'm just gonna keep ahead for just a second. Okay. All right. Now, as we know, to find the magnitude of the straight line velocity on a link that is rotating, we have to take the rotation into consideration. So the slower or the faster that this is rotating is going to affect what the straight line velocity magnitudes are. Okay. And that is through this relationship right here. Our straight line velocity, I should put my little tail on there. My straight line velocity magnitude is going to be equal to the angular velocity of that point on the link that it's on multiplied by radius r. Okay. Now let's talk about r. R in this case is going to be the distance from the center of rotation, or the radius to where that velocity is. So if I look here, this is going to be Rx, okay? The radius to point X. This, from the center of rotation, is going to be Ry, okay? The distance of point Y from the center of rotation. And as you can imagine, this is going to be Rz. So if I am trying to find the velocity of a point along that link, whether it's X, Y, or Z, then I have to make sure that I have its corresponding radius from the center of rotation to each one of those points. Does that make sense? Okay. So if this is the velocity of X, I'm going to take the W2, because it's on link number 2, multiplied by radius Rx. Okay. If it's Vy, it's going to be W2, because it's also on link 2, but it's going to be multiplied this time by Ry. And then you're going to notice that we have velocity of Z would be W2 times Rz. Now, we can see that those radiuses keep getting larger the further away from the center of rotation that I'm at, right? If this W remains the same for each one of these because it's on the link, right? Because W remains the same for every point on the link. But the but the radius, that distance away from its center of rotation, increases. Do you see why I'm showing VZ as the longest vector and VX as the shortest vector? You see that? So the further away from the center of rotation, my straight line velocity increases, right? The closer to the center of rotation, my straight line velocity magnitude decreases, right? So I would expect that Vx is going to be a smaller number than what Vz would be, right? And Vy would be in between those two, okay? All right. So this should be review. Are there any questions right now, kind of on the relationship that we see here? Okay. All right. Let's turn the page. This is where we're going to start filling some things in. Okay. Units. So we've already talked a little bit about units. You probably know some of these. So what we're going to do is you're going to notice that in the brackets here, we've got places that we're going to be putting information. So this is where we're going to start filling in now. And this is going to be something that you'll be handing in as part of your practice problems. If you don't have this printed out, you're going to have to kind of write these items out. Let me know what they're at and kind of duplicate what you see here and fill in. So straight line velocity in brackets here. Whenever you see me show units, you're going to notice that I always put them in the brackets rather than parentheses. Okay. It's just to kind of show that they're not, like variables. I just like, that you have the units here. So if I'm going to put units here for velocity, which would be a variable of v, what would be an appropriate set of units for velocity? Go ahead.
Feet and seconds.
What was that?
Feet and seconds.
Okay, you said feet and seconds. Okay, I need more. That's okay. Where would I put feet here? Top or bottom?
Oh,
On top, yes. So Laura said feet on top, and where would I put seconds? On the bottom. So how would I say that as a fraction? Feet
per second.
per second. Exactly. Yes. Yes. So distance divided by time, feet per second. So that's one set of units. Go ahead and fill that in. What's another set of units that we could use for velocity? Miles per hour. Yes, we could put miles would be our distance on top, right? And per hour, HR or H would be our time on the bottom. What's another valid set of units? Virtually anybody in the
Meters
chat
per
box.
second.
Put an option for units for velocity. And it's important that we know meters per second. Yes. Distance, meters over seconds. Excellent. Any others? Kilometers per hour. Absolutely. Distance, kilometers per hour underneath. So you kind of get the idea, right? And it's important to understand what the final units are going to be, because as we set up our problems, we're going to be putting our units in place. And then we're going to be looking at, okay, what are the units that are left? Are they velocity units if we're solving for velocity, for instance? Okay. The next one that we have here is radius. So thinking of a distance, what would be appropriate units for distance? And we're going to see that as a lowercase r.
Inches.
Inches, yes, inches would be good. What else would be good? Any distance units. Inches. What else can we measure units or distance in?
Feet.
Feet. What else could we? Yep, I got feet on miles. Yes. Yards. Absolutely. Meters, right? If we're looking at English or the metric system, centimeters. Absolutely. So any one of those we can put in here. Okay. Good. Angular velocity. And this is our W. What are units that we would see for angular velocity? We didn't talk about them yet. Angular velocity. Think about over here, right? Our W, we're going around in a circle. Steve.
It would be like feet per second squared.
No, that's acceleration. So Steve said feet per second squared, but good try. Good try. Feet per second squared is acceleration. Okay, that's going to be how much your velocity is changing. Okay, but good try. We're turning around. Okay, say that again. Radians per second. Yes, that is a version of, and we're gonna put that in here. Okay. I'm gonna put it as two of them. I'm gonna put radians per second. And I'm gonna put a little line in between, or a little squiggly, because this can be like an or. What are the other units that are more familiar? Nope, not degrees.
Revolution.
Revolutions per minute, or RPMs, right? Yes, but we're gonna put rev per minute underneath. Okay, so here, just because I was really looking for definitively revolutions per minute here, but radians per second, revolutions per minute are both valid units. So I'm going to put an or in here, or revolutions per minute are both valid units, okay? All right. Now, when we look at rearranging for our W here, okay, so as we know from the previous page, we can say that velocity, straight line velocity, is going to be equal to angular velocity times r. If we rearrange this algebraically to solve for W, okay, that means I'm going to take my r, I'm going to divide it on both sides, and I'm going to get W, or angular velocity, right? This is angular velocity. Angular velocity is going to be equal to straight line velocity. That's what W is, straight line velocity right here. I could actually go like this. Straight line velocity, V, divided by the radius or the distance. So units for velocity, we know to be, and we'll use units that are consistent. We're going to say feet per second, okay, divided by feet, right? So we're going to take the same units for our distance for radius as the same distance units in our velocity, okay? Now, this is where if we cancel out the units top to bottom, so what's in the numerator in the velocity and in the denominator here would be feet would cancel out, right? See that? Seconds don't cancel out. They're in the denominator. So the numerator to the denominator cancel out here. Everybody see that? Okay. Now, if we do that, we are left with nothing per second. Do you see that? Because our feet canceled out. But what magically appears, do you guys remember this? Radians. Okay. And it's because we are doing angular velocity or rotational speed here. Okay. All right. So radians magically appear, I say. All right. Radians magically appear. So when it's nothing per unit of time, it's radians per second. Okay. Radians per second. Now, many times W is going to be given to us in RPM. So for instance, it might say, hey, link number 2 is rotating at 100 RPMs. What is a straight line velocity component of the end of that link? Okay. Now, when it's given to us in RPMs, we cannot use it in this equation. We need to convert that RPMs to radians per second in order to use it in our equation relationship that we see here. So whether it's solving for W or if we're using W in the problem. So we have to kind of practice converting from RPMs or revolutions per minute to radians per second. And we have to also practice going from radians per second to revolutions per minute, because when we get it as a final answer, it doesn't mean anything to anybody. Okay. And we'll see that in the examples here. But before we start using an example, let's just practice converting here and kind of remember how we do this, because I'm sure you've done it along the way. So if I want to find out how many radians per second is the equivalent to 500 RPMs. So 500 RPMs is equal to how many radians per second? First of all, we are not going to write it as RPMs. We're going to write it in its fractional equivalent up-down method, if you would, okay? We're going to say, okay, 500, and I'm going to expand out. This is going to be my revolutions. The per is the horizontal line, and then the minute is down here. Does that make sense to everybody? So when you're doing a conversion for RPM, you are not going to start out with 500 RPM. You're gonna expand it out, and it's going to be revolutions on top, minutes on the bottom. Okay. And then we're going to do a conversion method that I think it's officially called the ratio method. Okay. And this is where now what we're going to do is we are going to fill in, I'm going to call it top bottom ratios of the equivalent values until we get to radians per second. So the first quantity I'm going to use here is going to be, I like to start on the top. So I'm going to have my 500 revolutions on top. Now, the other thing before we get into the up down here, if I have a whole number, that means that it's over 1. Okay. So 500 will be on top with the revolutions here, okay? And then per minute underneath. And it's per 1 minute if you would. So 500 revolutions. I'm going to get the revolutions in radians first. So do I know how many radians are in one revolution? Gosh, Lars, you're good. 2 pi radians in one revolution, or we can say 2 pi radians in 360 degrees, right? If you've heard it that way. So 360 is one revolution all the way around. So yes, I have revolutions. I know that 2 pi, I'm just going to put it on the side here. 2 pi radians equals one revolution, right? That's a conversion, right? So now I want to say, okay, now remember, as I go across here, I'm going to multiply across the top, divide by the bottom, and I want to cancel out. I want to get rid of revolutions. So I'm going to put it on the bottom down here. So I know that one revolution is equal to, and directly above it, I'm going to put it what it's equal to in radians. I know it's in 2 pi radians. Do you see that? Okay. So this ratio right here, put revolutions on the bottom because revolution was on the top here. Because when I multiply across the top, divide by the bottom, revolutions is going to cancel. Do you see that? Now I'm in radians per minute because radians hasn't canceled out yet. But I don't want to be in radians per minute. I want to end up with radians per second. So now I need to get my minutes in seconds. The minutes are in the denominator here. If I did RPMs, I wouldn't know that. Do you see that? That's why I have to expand it out. So now that means that minutes have to go on top here since it's in the bottom. 1 minute. And underneath, how many seconds is it equal to in 1 minute? We know this.
60.
60. Excellent, Garrett. Thank you. 60 seconds underneath. Now, if I multiply across, divide by the bottom, minutes cancel out. And the only things that aren't canceled out are radians on top and seconds on the bottom. If I look at the units that I want to get, radians per second, this is the units that I want. This confirms that if I multiply 500 times 2 times pi and then divide by 60, I'm going to end up with the appropriate units of radians per second. Do you see that? How many have done this version of conversions before? Okay, little bit. Well, guess what? This is how you're going to do them all the time for me. You will no longer be going on Google. You can confirm it with Google. I don't care. But I don't want anybody to be like, well, you just multiply by this to get this. No, no, no. You're writing it out. Okay. We only need to know a couple of conversions, all right, along the way. And we can do this. By doing it by the ratio method, you don't have to wonder, do I multiply by this or do I divide by this? You have it written out. And if you end up with the appropriate units top and bottom for what you have coming out over here, you know you set it up correctly. And now all we're going to do is we're going to multiply across the top. So 500 times 2 times pi, divide by 60. And what do I get for my radians per second here? Anybody do that yet?
52.
50, I got a 52.36, 52.36. Is that confirmed here in the room? Okay. So 52.36. Okay, and that's going to be radians per second. And this would be my final answer then. Okay. Let's go in the opposite direction. Let's do 10 radians per second is equal to how many RPMs? Okay. So, because we have to go between the two. So if I have 10 radians per second, so again, you're going to notice here that when I write this out, 10 is going to be over 1 because that's a whole number. So it's going to be, if you would, on top with the radians, and the per second is going to be underneath. Don't write it as a slash. Do not write it as a slash. Radians per second, top, bottom. So now, if I want to get to revolutions per minute, okay, so revolutions have to be on top. That means that I got to use this conversion up here. I know there's 2 pi radians and 1 revolution. So that means radians is going to go on the bottom, 2 pi radians, and 1 revolution goes on top. My radians, as I look here, top to bottom cancel. And now I'm in revolutions per second, right? Those two haven't canceled out yet, but I need to get in revolutions per minute. So since the seconds is on the bottom here, I'm going to put seconds on top. I know that there are 60 seconds in 1 minute. So the minute is going to go on the bottom. Seconds cancel out top to bottom, and my uncanceled out units are revolutions on top, minutes on the bottom. So revolutions per minute. And now here again, I don't have to worry about, do I multiply by 60? Do I divide by 60? I think if you write it out, you won't go wrong. So now you're going to take 10 times 60 divided by 2 divided by pi. How many revolutions per minute is 10 radians per second? Rainer. 191. Okay.
95.5,
You got what?
95.5.
95.5, 95.5, double check. Did you divide by 2 and divide by pi?
Forgot.
Okay. Yep, don't forget the 2. So it sounds like 95.5, 95.54. Yep, 95. That sounds good. That sounds good. Okay. Anybody else get that same thing? Yep. And then just remembering to divide by your 2, because there's 2 of them underneath there. Okay. All right. Now, once you get to the end here, if you have revolutions per minute, you can write a final answer as RPM. That's okay too. All right. But if you're in a conversion mode, you have to expand it out and put revolutions on top and minutes on the bottom. Okay. So questions on the conversions at this time? Okay. All right, cool.
Oh, it makes sense.
Oh yeah, go ahead.
Sorry, I was just saying, no, I got it. It makes sense.
Oh, you got it. Okay. All right. Very good. Okay. Then let's turn the page. We're going to do an example related to this. Okay. So our example says, determine the straight line velocity of point B as line 2 or link number 2 rotates 100 revolutions per minute counterclockwise. Okay. So we're going to set this up. We're going to set this up together. So information. It says that link number 2 or line number 2 is going to rotate at 100 RPMs. Okay, 100 RPMs. So we know that angular velocity of a link W has units of 100 RPMs, right? And it's telling us that it's going to be rotating counterclockwise. So I am going to show my angular velocity as an arc, okay, like this. And I'm going to label it W2. So it's the angular velocity of link number 2 or line number 2 here. Now you'll notice that it rotates about a fixed center at point A, right? Now, I need to put an arrowhead on here. Am I going to show the arrowhead on the left-hand side of my arc or on the right-hand side of my arc? Counterclockwise. Yeah, the left side, right? So it's going to be rotating in a counterclockwise direction, okay? And actually, I'm going to erase this. I'm going to push it over just a little bit. So I know that W2 is equal to 100 RPMs, right? And it's going counterclockwise. So if you wanted to put that right next to it, that's totally fine. Okay. Now we want to determine what is the straight line velocity of point B. Straight line velocity is going to have that variable of lowercase v. So if we look on the the first page here, okay. Remember, this is the straight line velocity of point X, Y, and Z, right? So this is going to be the straight line velocity component or the straight line velocity of point Z in this case. I want to do that very same thing for point B, okay? So to do that, what I'm going to do is I am going to create a line that is going to be represented by this V, and it's going to be perpendicular to the radius back to its center of rotation. So if this line right here is its radius, right? My velocity of B, I'm going to kind of put it over the top here, is going to be perpendicular to that line, and it's going to point in the direction of rotation. Remember, it's going to point in the direction of rotation perpendicular to its radius line back to its center of rotation. And this is going to be velocity B. And you want to label it. Okay. Straight line velocities are always perpendicular to the radius back to its center of rotation. Okay. So if we take that line straight back, V is going to be perpendicular to it. Okay. So VB is going up and to the left. All right. Now, to determine that straight line velocity, we're going to use that relationship from the first page. We know that V is equal to W times R, or angular velocity times the radius. Now, it's in the form that I need it in, right? So we are going to write it as VB is going to be equal to W2 times RB. Now, we don't see RB on here, do we? Remember, R is that radius from the center of rotation to the point that we're interested in, okay? So our RB, is it here? It is, right? Which number?
10.
10, yes. So this is going to be equal to RB. Yep. Okay. So it looks like we have everything we need, right? Okay. So let's put our numbers in. So W2, 100. And remember, we got to put our revolutions per minute. We're going to expand that out, right? Times 10 inches. So if I multiply this out, my velocity at B is going to be 1,000 revolution inches per minute. Is that good? Put a box around it. We're good to go. You guys like those units for velocity, straight line velocity, revolution inches per minute? I don't like them at
No.
all. Let's erase that. Okay. You guys aren't handing this in. That is wrong. I know. I know. This is something you don't want to do. You are not going to take RPMs and put them into this equation. What are we going to switch it to? Radians per second. Remember, on the previous page here, it said you need to convert to radians per second to use in that equation. So whenever our W is given to us in RPMs, and it will be, we deal in the world of RPMs. We don't deal in the world of radians per second. If you go to the motor store and you say, I want a motor that is 100 radians per second, they're going to be like, ah, that's nice. Thank you for telling me that. But what do you need in RPM? Or if you're going on the internet and you're trying to order a motor, you're not going to order it in radians per second. You're going to order it in RPMs. Okay. So it's very typical to, and you can relate to RPMs, right? I mean, a radian per second is like, but if I say 100 revolutions per minute, I get a feel for that, right? Like how many times I'm going to go around in a minute. So we want to convert this to radians per second to use in our equation. So the first thing we need to do, and I'm going to do that over here, I'm going to do my conversion. I need to say W2 is equal to 100 revolutions per minute. And I am simply going to convert that to radians per second. Okay, so over here is going to be my conversion. And if you need to go back and look, we did this in that first example, 500 revolutions per minute, right? So you'll notice that we have revolutions on top, minutes on the bottom, and now we're going to use that conversion. 2 pi radians is equal to 1 revolution. So 1 revolution goes on the bottom, 2 pi radians on top. Revolutions cancel. Okay. Now I'm in radians per minute, but I want to get in radians per second. So now I need to get my minutes. 1 minute is equal to 60 seconds, right? Minutes cancel. I'm in radians per second. Okay. So now go ahead, take 100 times 2 times pi, divide by 60, and our W2 is going to be a number in radians per second now, which is the value we need to use. And then let me know when you get a number. Steve?
Yeah, 10.47.
10.47. And what are the units?
The rad per second.
Yep, radians per second. Anybody else get that? Confirm that, 10.47. I'm seeing nods in the room. Excellent. Thank you, Aiden. Okay, so now this is the value. This one right here is going to go in our W2. So now we're going to say, okay, 10.47 radians per second, and put the units top bottom inside of this equation. Do not do a slash. Don't do radians slash seconds. Okay. And then I'm going to multiply by my RB. I know that my radius out to B, the distance from the center of rotation to point B, is 10 inches. Okay. So my velocity at B, if I take 10.47 times 10, that's going to be 104.7, right? Is my number. Units. Is this going to be radian inches per second? No. What happens to radians? They're unitless. They are like Lucky Charms. You're going to remember this forever. Whenever they are multiplied by something else, they magically disappear, like Lucky Charms. You remember that? Do they still have that commercial for Lucky Charms? They magically disappear because they're so delicious. They're magically delicious and they magically disappear. So, so this is going to be inches per second, okay, which are appropriate units for velocity. So the radians disappear, all right? Whenever we multiply radians by something, that something is what stays, okay? All right, so 104.7 inches per second is the velocity, the straight line velocity component of point B when this is rotating at 100 RPMs. Does that make sense? Okay. All right. Cool. Let's do another example. We're on a roll. Example 2, determine the angular velocity of link number 2. Angular velocity of link number 2. So that means we want to find W2, angular velocity, rotational speed, angular velocity. Okay. What is the angular velocity, W2? So we know that W, angular velocity, is how fast this is going around, right? What are the final units we're expecting for angular velocity? RPMs, right? We're going to report it in RPMs, but in our equation, what is it going to be? Radians per second. So we are going to report this, and I'm just going to kind of put this in parentheses. Radians per second we want to get to, right? Which then is we're going to, like I said, we're going to report out in RPMs. So if we wanted to buy the motor to rotate this at this, angular velocity, we can do that. But in our equation and out of our equation, we're going to be getting RPMs, or I'm sorry, radians per second. Okay. As I look over here at my diagram, so we're going to find W2, okay? Let's look at our diagram. As we look, you'll notice that there is a vector coming off of point B, and it is identified at 25 or 250 inches per second. What variable is that? What variable would we call that? Somebody has said velocity. Could that be velocity? Yes, you are correct. It is velocity, but velocity of what? Straight line velocity of what? Point B, exactly. So I'm going to put a VB right in front of that. Okay, VB is equal to. So that's our straight line velocity component. How do we know that? Two things. Number one, it's represented by a straight line with an arrowhead, right? It's a vector. We know that that's a vector quantity. Additionally, its units are in inches per second, distance over time. That's straight line velocity. Okay. 15 inches. What is that to us? I mean, it's a distance from the center of rotation, but if we look at our equation, which variable is that? It's the R, right? It's the radius to center of rotation. So we're going to call that RB again, right? Now, if I wanted to represent W2 over here on my diagram, I'm going to show it as an arc, right? About point A here, because it's going to rotate about that center. I'm going to call this W2, okay? the angular velocity of link number 2. Now, which way am I showing my arrow? Clockwise or counterclockwise this time?
Clockwise.
Clockwise. And if I put my finger on A here and I rotate in the direction of the straight line velocity, which way is my paper going? Clockwise, right? Remember, this straight line velocity has to go in the same direction as rotation. So if I know the straight line velocity, my rotation has to go in a clockwise direction according to this, okay? Okay. So now, if I want to solve for W, I can rearrange this equation again, right? Okay. W is equal to, W2 is going to be equal to the velocity of B divided by the radius of B. Okay. So I'm going to say equal to, my velocity of B is 250 inches per second, right? That's going to go on top. My radius of B is 15 inches. Inches cancel out top to bottom. Magnitude of W2. What is my number here? So it's going to be 250 divided by 15.
16.67.
16.67. Anybody else get that number? Yeah? Okay. 16.67 units. Units. My inches canceled top to bottom, so I have nothing per second. What are the units out of this equation? Radians per second. Remember, when there's nothing, radians now magically appear. Amazing. They magically disappear and they magically appear, right? So when it's nothing per second, unitless, radians per second. We're rotating. It has to be radians. Don't magically put in revolutions per minute because minutes aren't in there and revolutions aren't in there, right? Remember, in and out of this equation, radians per second. Yes, Aiden, thank you for putting that in. Now, that's nice and all, right? But if I wanted to specify a motor and I go to the motor store, I'm not going to say, I'd like a motor that's going 16.67 radians per second. I want one that's going at something RPM, right? Go ahead and convert this to RPMs. Okay, do that on your own. And then we'll kind of do it together. So kind of write it out like we did on the previous page so that we can take these radians per second and we can then convert them to RPMs because you're going to report out any angular velocities in RPMs. You're not going to stop at radians per second. Okay. So the one that probably you just have to remember that's not quite as familiar is the 2 pi radians equals 1 revolution. So when you put your units in place here, radians are on top, seconds are on the bottom. That's why we have to put them in, if you would, fraction form as opposed to the slash, okay? Top, bottom. So underneath here, I'm going to put in my first area. Now, for conversions, I always use vertical lines instead of parentheses to really kind of show it's a unit conversion. It's not part of an equation. So 2 pi radians on the bottom equals on top 1 revolution. So radians top to bottom cancel. Now I'm in revolutions per second. So I'm going to do one more. 60 seconds on top so that it can clear top to bottom is in 1 minute underneath. So seconds cancel. I have radians on top, minutes on the bottom. And my W2 is going to be 16.67 times 60 divided by 2 divided by pi. What do I get for my answer?
You know, 59.2.
We got 159.19, did you say?
Yeah.
19. Anybody else get that number? I've got nods. Okay, excellent.
Yep.
Awesome. Thank you, Garrett. So that's going to be revolutions per minute. Now, at the end here, if you want to write RPMs, I'm fine with that. But when we are, oopsie, rep, RPMs. When we are in the conversion mode, you have to expand it. Does that make sense to everybody? Okay. There we go. 159.19 RPMs. Okay. A lot of students will say, well, what if I leave my answer in radians per second? Points off. I'm sorry, because I want you to understand that the accepted units in, like specifying things are RPMs, not radians per second. Yes, they're equivalent, but it's not what we, if you would report out in. Okay. Okay. Any questions kind of on, these two looks right now, the relationship between straight line and angular velocities? See.
For the conversions, do you want the line shown, or is it all right if we do in the parentheses?
I'm okay with the parentheses. You'll just notice that the question was, do you want the lines, like vertically here? You'll see that I always write it out this way because that way, again, it kind of shows that this is a conversion as opposed to a part of the equation. So parentheses are okay as long as we see everything here and then the cancellations occur. Okay.
I know this isn't like totally relate to the class, but if I got like a steel bar going at 159.2 revolutions per minute, that 159.2, how does that like relate to the safety factor with the safety factor?
Yeah, I'm not exactly sure because so you asked about safety factor. Well, we would have to be looking at, so when we get to and although for you guys in mechanical design, you guys don't take dynamics. Dynamics, we start looking at the inertia created by whatever the size of the bar is. So we would have to know like how thick it is, how wide it is, and then how fast it's going. And then we can take that and we can start then, determining what is the angular momentum that is built up. And then that's going to then help us size elements that are here and such. But
There's a bunch of stuff.
well, because it's moving. Now in statics, we didn't have to worry about things moving, but because this would be rotating around and we wanted to maybe size some elements here, now we have to kind of go a little bit further with the analysis before we can then size things out. So there is more because it's moving. Yeah. Other questions? Okay. So what we're going to do, this is kind of a nice little natural break. We're going to stop in the handout at this moment. We're going to take our class break and then we're going to come back and we're going to move on for a little bit more. And then we'll stop for the day. Okay. So let's take a break of about 15 minutes. So come back at about 1:30 and we'll continue on with the second part, if you would, of our lecture today. And then we'll look at what you guys can work on homework wise.